Hello, my name is Sean Ditchko with the University of British Columbia Physics and Astronomy Department. In this video, we'll talk about nuclear fission and beta decay and how these relate to the problems at the nuclear reactor in Fukushima. In the last video of this playlist, I introduced this chart of nuclides, and now we're going to use it to talk about fission, and we can do that by clicking on this 235U, and Fy stands for fission yield. What's being yielded by the fission of uranium-235? And this is the answer. All of these nuclides. When a particular uranium atom fissions, you can only make predictions about what daughter isotopes will be produced, and you know that they'll be somewhere in this region here. And these colors indicate the probability of the different nuclides. So the darkest red is the highest probability, as you can see from the legend here. And so it's most probable to get something like cesium-141 combined with maybe strontium-96 or something like that. As you get to lighter and lighter color, those nuclides become less and less probable. There's another name for these daughter isotopes. They're also called nuclear waste. And you've probably heard that this nuclear waste is radioactive. And how do we know? Well, we can look at the half-life perspective on this chart of nuclides. And if you recall, the fission products were all here, and this is all light green and pink and light blue colored, all showing that they have short half-lives. And a short half-life means it decays. And the type of decay that happens with these particular nuclides is going to be of type beta decay. And how do I know that? Well, we can click on the decay mode perspective. And now the chart will be colored by decay mode. We can see that all the fission products which were in this region are below this black line of stability and in a region that's colored pink, which means that these nuclides will experience beta decay. This legend has a beta symbol for the pink, which means it represents beta decay. And so the half-life perspective says the fission products decay quickly, and the decay mode perspective on this chart says here's the type of decay. It's going to be beta type decay. Now it's fine to have this chart tell us that the fission products are going to have beta decay, but wouldn't it be nice to know why the fission products are in this region, and also to know why those fission products are radioactive beyond just having this chart tell us? And there's some good reasons for it, actually. It turns out there's an ideal ratio of the number of neutrons to the number of protons in an atom. But it's also true that this ideal ratio changes depending on how massive the atom is. So if we take uranium-235, for example, we know that its atomic number is 92, and so we can calculate the ratio of neutrons to protons in this atom. Knowing that the atomic number of uranium-235 is 92, we can divide that by the total number of nucleons, 235, and then subtract away the number of protons, and this will be 92 protons divided by 143 neutrons. And this calculation gives us 0.64 protons for every neutron. And you can also take the reciprocal of this and think of it as 1.6 neutrons per proton. I prefer to think of it in this way, actually. So this says for every proton that you have in a uranium nucleus, there needs to be 1.6 neutrons there to glue it together. Neutrons are, you can think of as a nuclear glue. Through the strong nuclear force, they counteract this electrostatic repulsion between the many protons that are there. Let's compare this neutron to proton ratio with a lighter element like nickel, nickel-61 say. Nickel-61 has 28 protons, and so we'll calculate the ratio over here now. So this work here before was for uranium, and now we'll talk about nickel. So nickel has 28 protons, and we're going to divide that by 61, subtract the 28 protons, and this gives us 28 protons for every 33 neutrons. It's almost a 1-to-1 ratio, quite different from the uranium. This is approximately 0.84 protons per neutron, and if you take the reciprocal of that, 1 divided by 0.84 is 1.2 neutrons for every proton. So it makes some intuitive sense here that we have a lighter or smaller nuclide, atomic number 28, and it needs only 1.2 neutrons to glue each of these protons together. Whereas with the uranium nuclide, you have so many protons and so much electrostatic repulsion between them that you need 1.6 neutrons to bind each of those protons together. So this ratio, 1.6 versus 1.2, is what changes as you move along the chart of nuclides. And this is going to help explain why the fission products are radioactive. The next thing I'm going to explain is why fission of uranium produces daughter isotopes that have the same ratio of neutrons to protons. And then I'll explain that, well, that ratio is not ideal for these new lighter elements, and so that's why it's radioactive. Let's talk about fission. Why do the daughter isotopes have the same ratio of neutrons to protons as the uranium did? I'm going to draw a hypothetical uranium nucleus with pluses representing protons and O's representing neutrons. And I'm not going to draw all 92 protons and all the rest of those neutrons. I'm just going to draw 16 neutrons and 10 protons. And the reason for that is that 16 neutrons divided by 10 protons equals 1.6. So the model that we're working with here has the same ratio of protons to neutrons as a real uranium-235 nucleus has. Now let's illustrate what happens in fission. A neutron comes in and stirs things up. It knocks up this nucleus into two parts, and I'm drawing symmetric fission here, which doesn't actually happen very often. Typically it's asymmetric in that there are more protons and neutrons in one half than the other. And the other detail I'm neglecting is that these neutrons are shot off as free neutrons, which go off to hit other uranium nuclei and split them apart. Just to illustrate my point though, that we have here 1, 2, 3, 4, 5, 6, 7, 8 neutrons. So there are 8 neutrons in this daughter isotope. That's what I've drawn here. This is a fission product of this process. And so we have 8 neutrons and then 1, 2, 3, 4, 5 protons. And 8 over 5 makes 1.6. And over here we also have 8 neutrons and 5 protons, also giving the ratio of 1.6. And so my point is that the daughter isotopes have the same ratio of neutrons to protons as the original uranium nucleus did. Now on this chart of nuclides, the ratio of the number of neutrons to protons is the slope of the line joining the nuclide with the origin. Whatever ratio the uranium has, every other nuclide that's on this line joining it with the origin has the same ratio. And the fission products, as we've demonstrated, will have the same ratio, and so they'll be on this red line. And this red line passes through a region of short half-life, a region of radioactivity. And so I'm explaining why the fission products are here, because these are all the nuclides that are on the line joining uranium with the origin, or in other words, they have the same ratio of neutrons to protons. And this region is not an ideal ratio for lighter elements. And so lighter elements prefer a ratio that's slightly different. So they shouldn't be on this red line if they're going to be stable. And this kind of explains why fission products are radioactive. They have the wrong ratio of neutrons to protons for elements of this particular lighter mass. An interesting trend you can see on this chart of nuclides is the curvature of this region of stability. All these black squares represent stable nuclides, and they lie on a curve. If they were on a straight line, it would look more like this. That would be a straight line. So you can really see the departure from that line as you get to more massive nuclides. So all these ones at the beginning tend to fall in this green line that I've created, but over here, the ratio of neutrons to protons is different for the massive nuclides. They require more neutrons for a given proton. Uranium up here had 1.6 as its ratio versus nickel down here had 1.2 before. If nature was different and this region of stability did lie along the straight green line, then the fission products of uranium would not be radioactive most of the time because they would have the same ratio as the uranium, and that would be along this line of stability. It'd be a completely different world if this was not curved. Now I wanted to talk more about beta decay, and I'm going to use cesium as an example. Cesium-137. You hear about this particular nuclide in the news, along with iodine-131, by the way, but let's talk about one at a time. We'll talk about cesium right now. I'm going to zoom in onto zoom level 2. Cesium is a particular health concern because if you look at the periodic table of elements, cesium is in number 55. It's in the same family as potassium and sodium. Because it's in the same family, it has the same chemical properties as potassium and sodium, and it tends to get roped into the same biological chemical processes in the body as potassium and sodium do. And so this is why it's a health concern, because it doesn't get expelled as quickly as other things, because the body sees it as similar to potassium and sodium and uses it just the same. Now, why is it 137 isotope of cesium that you hear about in the news? Why not 136 or 138? They're all being produced by this nuclear fission. Well, if you look at this chart where it shows the half-life, you can see that 137 has a half-life of 30 years, whereas 138, which you don't hear about, has a half-life of 33 milliseconds. And that's why you don't hear about it. It disappears so quickly. Same with 136, it has a half-life of only 13 days, which is not that long, and so it's not as much of a concern. This 30 years, though, that's going to be around for a while. Cesium-137 is a concern. Cesium-135 has a half-life of 2 million years. Cesium-135 has low activity. Activity is the word that describes the rate of decay in a sample of this particular isotope. And it's measured in units of becquerels. And 1 becquerel is 1 decay per second of a particular sample. So with such a long half-life, it'll have a low activity, low becquerels in other words, and it won't be a concern for this 135 isotope. For 137, however, it's in a bit of a sweet spot where, the half-life is a little bit long, 30 years, and so it's going to be around for a while, but the half-life is still short enough that the activity is fairly high. There's many decays per second, lots of becquerels, and so it's both high activity and fairly long half-life, and this is why it's a health concern compared to the other isotopes. Now, what exactly is beta decay? It's this spontaneous thing that happens where some nucleus with atomic number Z and atomic mass A suddenly turns into a different nucleus with one additional proton and the same atomic mass. What's happened is a neutron has turned into a proton plus also an electron, which zips off, and also an anti-electron neutrino. Here's a specific example. Consider cesium-137. It will turn into barium, which is the element with one additional proton, atomic number 56, and the same atomic mass, plus an electron antineutrino. And it's the energy of these products that are responsible for the problems in Fukushima. The energy ultimately turns into heat from these two things. This neutrino carries off lots of energy from this beta decay, but it does so harmlessly because it doesn't interact with matter very much. It just zips off through the planet out into space typically. But these guys will collide with other bits of matter around, and their kinetic energy will get turned into heat. In our next video, we'll calculate how much energy is released by this beta decay. And this heat energy is being absorbed by water that they're using to cool the radioactive waste. And we'll calculate that a whole ton of water is boiled off every few minutes, a few days after the tidal wave hit, and show that that's why they're having so many problems there, because it boils off so much water so quickly. There's so much heat being produced. That calculation is in the next video, so stay tuned.